right, for our last talk of the morning, I'm pleased to introduce Kobi Kremnitzer from Oxford, who will speak about functional analysis over the integers, L functions, and global Hodge theory.
Thank you very much. Thanks for inviting me. It's great to be here. Yeah, so my talk will be a slightly different flavor from the other talks. Analysis. Z, L functions, global Hodge theory. So this is kind of work in progress. So it's joined with Jack theory and Federico and Bambozzi. So I'll describe this kind of work in progress. So you'll see there something I can tell you, and then there'll be lots of questions, interesting questions that I don't know. But it's based on already kind of existing work that will appear on the archive, let's say, in probably 2-3 weeks, with so based on work with and Oren and Massa, which is kind of a foundational work on how to do analytic geometry over any Banach ring, and not just analytic geometry. Lots of types of geometry is kind of in great generality. And so the starting point is kind of well, I'll just say a few words about what bornology is. Somehow, kind of, it's really going to have a long talk about the history of mathematics. So, which I would say kind of took the wrong turn. So, you know, and you all know about topologies, right? And in topology, kind of the basic notion is kind of being continuous. And then there's often, and when you learn functional analysis, you learn kind of basic theorems like, well, continuity or maybe implies boundedness, and sometimes for nice enough spaces they're equivalent. So that's kind of like some important theorems in functional analysis. So reals or p-adics. And kind of just to give some flavor, really what's going on here, I would say that continuous, well, so of course this depends on the notion of an open subset. From kind of a category theory perspective, this is kind of, you'll see this has to do with some kind of taking a plural completion of some category, maybe norm spaces or Banach spaces. And this boundedness has to, you know, it's a notion of bounded subsets. And from a category theory perspective, this has to do with an incompletion. And I would say kind of why did mathematics take the wrong turn? So if you care about doing algebra, incompletions are good, and pro-completions are usually messy. So it's much easier to do kind of algebra in this setting. And if you can do algebra, you can do geometry, at least versions of algebraic geometry, which is hard to do here, right? So when you learn like different forms of topological algebra, you see how people work really hard to define everything. And for Shea cases, you do something like this. Dual for Shea cases, you do something slightly different. And then it kind of works, and it's very ad hoc. Here, it just works for everything. So that's why it's good. So just to remind, so what is a bornological set? So you just have a kind of a collection of bounded subsets. Or kind of, you might call bounded subset, and of set X. So, well, you want kind of the points to be bounded, right? So here X is X, and you want to say that, well, if A is bounded and B is a subset, then B is bounded. That's natural to assume. And you also want to say that the finite union, so if A1 AN bounded, and so is the union of AR. So that's the notion of a bornological set. So clearly you can then talk about, if you have two of them, you can talk about bounded maps, right? So if from X to Y will be bounded, if it sends bounded subsets, the bounded subset. So you get a category, bornological set. We can call it maybe Born. And so one kind of one way of viewing this is really what is this thing? Well, it fits very nicely to subcategory kind of, where what you do is you take the category of sets. So now I won't talk about size issues. So kind of, I need a small category. So take some kappa or something like that, and like some sets, small sets. And you take this kind of sifted co-completion of this, right? So in other words, kind of, so this is the subcategory of the pre-sheaf categories of pre-sheaves that commute with finite products. This is the sifted co-completion. I mean, notice that if I take finite sets, then I just get the category of sets, right? But so you can think of, from a category theory perspective, this is what's going on. And then, you can do some abelian group objects in here, or other type of things, and kind of develop algebra and so on in this setting. Now, there's a problem if you do this.
Question.
Yeah.
So how does set sit inside? Maybe just could you parse for us? You think of set inside.
I mean, these are chaotic. I mean, everything is bounded.
Everything.
Yeah. Right. So essentially, kind of when you take sifted co-completion, in nice cases, kind of what you do is it's two operations. I mean, you first add some kind of reflective co-equalizers, and then you add filtered co-limits. So the idea is that kind of any bornology you can achieve in these two ways from the kind of things which are everything is bounded. So you can resolve things in this way. Now, the problem with this construction is that, like you see here, I mean, I want to kind of do function analysis over Z, and I want to do it in a way that kind of unifies Archimedean and non-Archimedean function analysis. So I can look at Z with its kind of Archimedean norm. So this kind of is responsive. This is the initial Banach algebra. So that kind of unifies Archimedean and non-Archimedean. Or I can look at Z with its kind of trivial norm. So that just sees the non-Archimedean part. But kind of you're throwing away the Archimedean part. But if you think about it, I mean, in terms of bounded subsets, they look the same. Right? I mean, they're just finite subsets of Z. If you're looking at kind of balls of finite radius, you don't see any difference. So if you just take this approach, it's not so good. I mean, you get a bit stuck. So a different thing you can do is you want to remember the radius. So it's not just enough to have bounded subsets, you want to kind of have some notion of how big they are. So the way to do that is kind of you replace it by something you might call norm set.
Why did you call the trivial one non-Archimedean?
If you think
Opposed to like p-adic
so from here, so from this Banach string, I can complete and get all the p-adic ones. So in terms of kind of the Berkovich tree, you can think
But
about.
then you have plenty of bounded subsets.
I'm just saying if I'm just looking at just at Z itself as for discrete. I mean the point is that for discrete Banach rings, this notion of bornology is too weak.
What does trivial norm?
I just one for it.
But then all sets are bounded if it's just one.
Well, I don't see, I mean, we can discuss this later. I mean, you'll see what I want to do. So I want to kind of look at norm sets where a norm set is just a set X with a function from X to plus, right? And then you can clearly define kind of bounded functions between such sets. Right, if I have like, well, I can write it like this, if I have X in a norm on X, and a map to Y, norm on Y, so it's H, then I can just say that this is bounded if there's some constant that if you look at, see correctly, that kind of H, X, norm and Y is less than or equal to some bound times the norm of X. Right? So this category is different than just looking at sets with functions on them, because we're only allowing bounded maps. And then again, I can take the shifted co-completion of this. And this turns out to be a good place to do stuff. So you can look at the billion group objects in there, or you can look at spectra in here. And actually, this is a good way of understanding kind of what bounded cohomology is from but we can discuss this will take time, but let's do something simpler, which we're just looking at Banach modules. But before we do that, I'll just give a short remark, because maybe you're asking yourself, how is this related to condensed sets, maybe? So, I mean, what happens with condensed sets is that you have this kind of filter monad on the category of sets, again, some small category of sets. Whenever you have a monad, you can take what's called its kind of Kleisli category of this monad. Let's say, in other words, I'm just looking at free algebras over this. So just objects of the form U of some set. And then you're taking the, so condensed is just the shifted co-completion of this category. Which, again, like I said before, you can think of this as being of U algebras, and you can see that U algebras are just compact Hausdorff spaces. So both, so somehow you see that these two things are very much related, but except that you turn on this filter monad, which makes things very complicated, right? It's kind of like these things are sort of, well, certain bornological sets with a convergence structure. But giving this convergence structure is very difficult in general. That's why it's very hard to write objects in this category. So let's do something. There's a nice subcategory in there that is much easier to describe. And so let's look at this. I'll look at in so what is this? So, well, here I'm thinking of Z with its median norm. I can look at Banach modules over that, right? And I can take the int completion of this category. So it turns out that this is a very beautiful category, right? So I'll just tell you its properties. So, and actually it's true for any Banach ring, but let's just state it for here. So the thing about the Ban Z, well, it's quasi-Abelian, which is good enough if you want to do homological algebra. It has enough projectives. Tensor project. Well, I should say this category has this kind of muteness over time. It has a tensor product, the projective tensor product of Banach modules. So tensor product of projectives is projective, and projectives are flat. It's easy to verify all these properties, and it turns out that actually, whenever you have an exact category of these properties, you can do geometry and everything. Just in algebra, everything just works very formally. Now, the only problem with Ban Z is that it only has finite limits and colimits. That's the usual problem with Banach modules. So you just int complete it. just formally add co-limits. And this category has all kind of small limits and co-limits. So that's the category where it will work. And you see kind of it's there. These things, I'll give you examples, we can write very explicit objects in there. Yeah.
How far is this from being stable in 3D category?
I mean, this is it's not an infinity category. I mean, it's a one category, but you can take its derived category and or enhance
Would
derived.
that be stable, or how far would that be?
It's not a, yeah. I mean, depending on which version of the derived category you take. So just let me give you kind of examples of objects in there. So for instance, we can look at functions on the closed disk of radius R. So this is a Banach algebra. So these will be just kind of let's say formal power series where the AN are integers, and they converge. So for radius R. So it's kind of a summable sequence in the Archimedean sense. Now from this, we can construct lots of other algebras. So for instance, if I want functions on the open disk of radius R, I can just take the limit. So I told you this category has all limits and co-limits, kind of for, let's say, epsilon less than R, for functions on closed disk of radius epsilon. Or another object we would like is kind of the dagger algebra over Z for disk of radius R. This is where we take the co-limit, epsilon bigger than R, of these things. And again, so when I write it like this, this kind of remembers how it's an object in BAN. But you can explicitly write the underlying set as just some formal power series with integer coefficients that either have a radius of convergence up to R, or that they converge for some epsilon bigger than R.
So when you define these Banach modules, do you require this to be a norm or only a semi-norm?
But for Banach, I require it to be a norm.
So in particular, you have to ignore all torsion, yes? I mean, you
Well,
have, they have to be torsion free, yes?
we can discuss this. So again, we can discuss this later. So and then if I take R to be kind of in some sense 0 or infinity, another object we can look at is like just let's say functions, analytic functions over Z on affine space. And or something that we would like is this dagger, which will be the germ. So this is kind of this is kind of the dagger thing for disk of radius 0, right? So just look at the germ at 0 of functions. So just formal power series with integer coefficient that have some radius of convergence. So this is this is an example. This will be actually in this context like this is a nuclear Frechet algebra, and this is a nuclear dual Frechet algebra. And they have like usual relations between them that you might like are true. So one is kind of they're dual to each other, and so you get that. And that's not difficult. Kind of the dual of this is just these functions, analytic functions in A1. The dual of analytic function in A1 is the dagger, this germ thing. Now, but another nice thing that happens is that if I take, let's say, one of these, suppose I look at analytic functions on A1 over Z. By the way, notice one thing, right? So this, when the radius becomes bigger than 1, being convergent just means that it's polynomial. But you're remembering all the kind of norms. I mean, you're remembering that, so it's not just the set, it's an object in this category. So
I'm confused what the category is. I mean, Banach usually means there's one norm, right? You're complete with respect to the norm. Then now in the examples, you're giving situations where you have kind of multiple different kind of spaces.
That's why I'm taking in, but
Okay.
yeah, I mean, the problem is that this category is only finally complete and full complete. So I need to allow myself to take kind of limits and co-limits of such things. So yeah, these algebras are not, like I said, this is a kind of Fréchet algebra. It's a countable inverse limit of Banach algebras. And this is the dual Fréchet. And you can also talk about nuclearity, which is important for other things. So that's what they are. They're not Banach algebra. So as a set, this is just polynomials. I mean, the germ is much more complicated. This is kind of very big, but still I can kind of use this. I said that it's a closed symmetric monoidal category. So I can, for instance, take the tensor product of this with C. And maybe it's not surprising, you would get just analytic functions over C on A1, just entire functions. But I can also take tensor product over QP. And the maybe surprising thing is that you do get an analytic function over QP on A1. Now, why does this happen? So what's going on here is that, well, okay, we wrote this as some limit or the dual fit as a co-limit of these Banach algebras, which use the kind of Archimedean summability, right? Now you can check that what happens when you base change to QP. If people doing kind of QP analysis know that usually you're working with non-Archimedean modules, right? Non-Archimedean Banach or ultrametric Banach spaces. You're allowed to work also with all Banach spaces over QP, so you don't have to assume that the Banach space itself is ultrametric. And so this inverse limit or the co-limit, actually you can sandwich between any two such, I mean, if you have a radius and if the radius is a bit bigger, you can put the non-Archimedean summability. So you get maps between these things. So you can rewrite this inverse limit or this direct limit in an equivalent way where you just use the non-Archimedean versions or what's usually called Tate algebras. And that would give you, that's why this is true. So even though we've defined it kind of in an Archimedean way, when we base change to a non-Archimedean field, we get the non-Archimedean definition. Yeah.
So you put A1 into the symbol of analytic Z. And I mean, just what kind of thing, just beforehand, are we allowed to put in there to?
So we can discuss this too, but you can analytify any scheme, or definitely any affine scheme, you can analytify it and get these.
So are these kind of the two statements you made? Are these really kind of special statements, or are they just something about?
No, it's not.
A scheme like
There's nothing special going on here. I think this was just an example of why, if you work in this context, you do get something that puts together Archimedean and non-Archimedean geometry together. So you can define, and that's kind of the point of this talk, to show you that you can define these objects over Z, kind of, somehow function analysis over Z, that when you base change to the complex numbers, you get complex analytic objects, but when you base change to the p-adic numbers, you get these p-adic analytic objects. So somehow the idea that Archimedean and non-Archimedean somehow are similar, but they don't really talk to each other is wrong. I mean, they do live in a family. You see that there's kind of problem. I mean, if you want to make this always true, you have some problems, but you'll see some more examples.
For David's question, I think for what you wrote for A1, you replace it with the disk, is it true?
So the closed disk is not true, right? Because you see, I mean, the argument, but if you do an open disk, yeah, that's okay.
And then translate at the top of that board, I'm surprised there are no divided powers.
No, they'll appear later.
Why don't they appear?
What's
What's the pairing between the two sides?
Oh, this is just, you have two formal power series. One, I mean, you can just pair them. It's just the usual, you can think about this in terms, again, we can talk about this later, but you just have a form power series with some radius of convergence and the form power, well, the polynomial in this case, there's just a pairing, right? Just you have AI and BI, and you just look at the sum of AI times BI. That's it.
And the standard product with C and QP commute with the limit, with co-limit.
With colimits, they always commute. So actually proving this for the germ is immediate.
Yeah.
It also in this case commutes with the limit. That's a slightly harder thing to prove. And also maybe another thing to point out is that in this language, right? I mean, these maps from let's say Z to ZP or from Z to R, they're kind of finite type maps, right? Because the way you get them is simply you take a Tate algebra over Z, one of these disks, and then you put x equals p, or you put, let's say, 2x minus 1, so you invert 2, you just get ZP or R as these maps. So they are just finite type maps. There's no kind of course, there's completion always involved because we're using this completed tensor product, but from the perspective of category theory, they're finite type.
And so the norm you use here is exactly the sum of an r to the n, yes?
Yeah. So it's the Archimedean summability. Yeah, more examples you can do. So, well, something that does appear. I mean, you can take this kind of this dagger or this germ, and you can kind of localize T1. You can sort of localize T. So this is some kind of a version of the overlay. It's got a proper ring of radius 0. But so this will appear. More examples that kind of I'm interested in is, so this is where interesting things happen. So let's look at integer valued polynomials, right? So just to recall, these are f in qx, f of z is z. So I think this is one of the most beautiful rings in mathematics. I mean, when you start looking at it, it appears in so many places, also in topology and so on. It's a beautiful ring. We'll use the fact that, so it has two coproducts. There's the additive coproduct, so I can just easily write this. So the coproduct of f, let's say, just is fx plus y, and the multiplicative coproduct of f is f x times y. So what do I mean by this? Of course, this is now an integer valued polynomial in two variables, but so this belongs kind of to int 2, which you can easily see as isomorphic to int counter int. The same with this. So really this int has what you might call a core-ring structure, right? In other words, if I look at spec of this thing, it's a ring, it's ring scheme, and it's a form of A1, but an interesting form of A1. So just some properties about this that we would need. So it has, as you know, it's neutral this, or there's a basis given by the binomials. And another thing that is important is that it has a filtration, where the phi is given by, well, span instead of x plus I, or let's say n I less than 9. So it's a filtered ray. And the associated gradient for this filtration is exactly the divided power algebra. So what we'll do is we'll look at the completion of this ring. So I'm allowing, so this again will be a bit funny, so I'll write it like this. So I'm allowing sums of this form where essentially I want that an t to the n is an entire function. This is just so essentially what I'm saying is, again, these will be finite sums, because remember, these are just finite sums over Z. But when you complete it, you get interesting things, right? So this is just a shorthand to remembering all these possible norms on this thing. So if you look at this thing over C, it turns out that people in the 1930s, 40s in approximation theory were looking at these kinds of rings, because this gives you exactly kind of analytic function of some exponential type on A1, we'll see.
So it's like a Borel summation, something like this.
It's not like the question is, which analytic functions you can write. You look at their Newton series, and when does it converge?
I mean, if you had divided powers, it would be like Borel summation.
Yeah, that actually will appear too. But if you you can take the same thing and convert it to E, and then you actually just get all analytic functions. And it's easier to converge there. And of course, these type of things often in let's say non-Archimedean analysis or p-adic Hodge theory, you use kind of radius 1 conditions. So the thing you'll see kind of in everything I'm talking about is that radius 1 only works in a non-Archimedean setting, right? If you want something that works globally, that combines both Archimedean and non-Archimedean, you can't use radius 1, right? It doesn't work in the Archimedean setting. Well, you can define it, and of course I can put some different growth conditions here to get the radius 1 version, which will then base change to maybe depending what I do, like locally analytic functions on a disk, but it won't have nice properties over the complex numbers. Now, another really interesting ring is this ring which is called stable or integer valued polynomials. So it's kind of similar. This, I think, the definition is like these are rational polynomials with a property that now say Fn is one over n, or allowing some denominators. And you can see that this is actually the same thing as int or just localized x, and it has a basis now given by x choose I, but also x inverse choose I. Now you might ask, why is it called stable? Why it's stable? Because I think it was, well, I'm sure algebraists thought about this, but kind of it appeared really in the work of topologists. So, I mean, the integer value polynomials appear when you kind of look at K theory of CP infinity.
Sorry, I don't understand. So f is an ordinary polynomial in x. So how can it contain x inverse?
Sorry, yeah, I should. I do have an inverse there. So, so you can look at the K theory of this. This is integer valued polynomials, but then you can ask what happens when you stabilize this. So you can kind of look at K theory of K theory, or K homology. I mean, get some cooperations on K theory, and actually you can calculate to get this ring. So this is why this is called stable for topology reasons. And then in a similar way, I can take some completion of it. So now, so all of these are kind of nice examples of rings, but I also want to do some geometry. So, okay, I didn't tell you, but if you have a symmetric monoidal category, a nice enough symmetric monoidal category, I can look at commutative ring objects in it, right? Take the opposite of that, call that affine schemes in this setting, and then define some Grothendieck topologies on that. I can then define schemes, stacks, geometric stacks, and so on. So I won't go into that. That's kind of the work that is already done. So this is all possible to do over any Banach ring, including Z. So in this context, kind of, I'll just call, so we have this GA, I'll call it arithmetic analytic. So this will be just kind of this spec of integer value polynomials with the additive coproduct. So it's a kind of an analytic group scheme over Z. And I'll have kind of a GM, again, arithmetic analytic. So this will be spec of the stable one with the multiplicative coproduct. And as you know, so like I said, you really get the form of A1, and then what you get here is that clearly kind of this GM arithmetic analytic acts on this GA arithmetic analytic, right? In the same way that GM acts on GA. I mean, the formulas are interesting, right? They involve kind of taking binomials and, well, you can write down how this thing looks like, for instance. There are kind of fun formulas that you can write down. Now, we also have, because of this filtration, we have the Riesz algebra of this thing with respect to this filtration. And now what I want to do is kind of, I want to define kind of a completed Riesz algebra of this thing. Well, I take the Riesz algebra with respect to this filtration, and I kind of base change it to the germ, right? So it's the kind of a micro-localization type procedure. So this thing, this Riesz algebra lives over the line, like on the algebraic analytic line, and you can, and I'm just kind of completing it over at the germ at 0. That's what I'm doing. Now, so we can define another kind of object, which we'll call GA arithmetic analytic filter. So this will be kind of spec of this completed Riesz algebra with the additive one. So you can take that this it's a filtered Hopf algebra for the additive one, not for the multiplicative one. Now, and it turns out that actually this action here extends. So we have an action of GM arithmetic analytic acts on this GA arithmetic analytic filter in a way which is compatible, right? So clearly this now sits over the dagger disk. That's by construction. And GM acts here. Now you might ask, how does it act here? So this is the usual formula of p-adic Hodge theory. So I have, let's say, called variable q, which will be 1 plus t. This goes to q to the x, right? Which is 1 plus t to the x, which of course you can write as a sum of x with n t to the n, which is an element in the tensor product. So this gives you kind of a map from the dagger to the dagger tensor, this int stable. So it's a co-action, which corresponds to just the action of this on the dagger disk. And you can see that it actually also acts. So there's some subtlety here because the multiplicative coproduct does not preserve the filtration. That's really why you need to look at the Riesz algebra, because it kind of, you have to move between the fibers. And the way to see the action, it's hard to write the formulas. The easy way to write the formulas is actually to see that this is actually, this thing here is this Cartier dual to something much simpler, which is, you know, in the same way that you can talk about formal group schemes or formal group laws, you can talk about, say, analytic group laws. Just use the dagger, this germ, instead of formal power series, and you just have the formula kind of x, the formal group laws, x plus y plus a, say alpha xy, where alpha is the parameter in the germ, and you can see, so when alpha is 1, there's a clear action of, well, actually, essentially the same action of GM on this multiplicative analytic group law. But then you can see that it also acts when kind of you let alpha vary. It's easy to write down, and you know, the pole cancels. I mean, that's...
So I have a question. Is this int hat? So int is a kind of classical example of a lambda ring.
Yes.
Which is universal actually. In one, so like free lambda ring in one variable.
It's the free binomial ring at one point. Okay. There's binomial rings and there's lambda rings, but I think it does, you can generate this is it's actually related. So, all of this started by trying to get global versions of things like prismatic and things like that, where you use bit vectors a lot.
Yeah.
Now, of course, you can always globalize this by using the big bit vectors. And the problem is that you get very big things that in some, the big bit vectors are really not a global, well, they are a global object, but they're just kind of almost just a product of all the local objects. So there's nothing that lives really in a family in a nice way. Now, it's true, and actually this is related, and you can see this, right, because of course lambda rings are related to K-theory, to BU. You can actually generate, in some way that you can use first Chern classes to generate everything using complicated formulas. You can generate lambda ring structure from the binomial ring structure. So in some sense, I would say kind of I think the correct global object comes from these binomial rings. And it does know about all the local things you'll see, but if you try to do it using bit vectors, I don't think you get the right definition.
But with vectors, so with vector functor is right adjoint to the functor of forgetting lambda ring structure.
Yeah.
And so does int head have a structure of lambda ring in your category, or?
So here's something that you can actually see. So again, we can do kind of duality, like Cartier duality for these type of things, and you can see that, well, what is a cohomology over this int hat? It's that because you can evaluate, of course, these things at integers, like positive integers. So if you use the multiplicative structure, not kind of what I call GM, then a module for that does give you an action of kind of n cross. So you get, it's a certain kind of action of n cross where the formula for this action is an analytic formula. That's what these things are. And so of course, lambda rings are certain rings with an action of n cross, let's say with an extra condition about the Frobenius. So you can now define analytic lambda rings using this. Yeah, you can do that.
And you will get some sort of analytic with vectors also?
Yes, you can. And we thought about, again, I don't know if that's the right thing to do, again, in the global setting. So, yeah, bit vectors are very nice locally, but globally, I'm not sure it's the right thing. So, okay, it's a hurry. So I'll just say a few words about L functions and how. So these are just a few lines of kind of easy observation or calculations when you use this language. So, right, for instance, with the Riemann zeta function, you start kind of with essentially a measure, let's say t, which is t over e to the t minus 1. And then you define kind of for each nice enough function, you can look at its Mellin transform. So this would be the Mellin transform of this f. And that sort of gives you the Riemann zeta function, right? And because you can do that, you see that it has an analytic continuation and so on. So now what is often done, right? So we do a change of variable like I did before. So let's call e to the t bq, which will be 1 plus t. So we're back to this German at 1. Now, often kind of you do okay, so of course now I can write this thing, but then I'll need to use log q, right? Suppose I don't want, we'll discuss this soon, but suppose I don't want to use log q. So you can regularize this in a different way. That's the usual trick in the chaotic setting. To define something, let's say fa of t would be something like 1 over e to the t minus 1 minus a over e to the t minus 1. So let's say a to be a positive integer, which under the new coordinates, this is 1 over t minus a over 1 plus t to the n minus 1, right? And the point is that, well, okay, now I can take the Mellin transform of that, and I get up to some factors, I get still the zeta function.
But when I take Mellin transform, you still need to use log I mean, this is integral of t to the s times this function. So we still have to use log t, so.
So I'm talking about the measures, kind of the, let's say the zeta measures. That's what I want to write over z. Then kind of when you pass to the Archimedean and non-Archimedean, you do different kind of transforms, but essentially a Melling transform in the relative setting. But let's look at the measures. That's kind of what I'm trying to, because of course the point is, you know, for some reason, you can, let's say you define the Riemann zeta function as some infinite product, let's say, and then it turns out that you can write it as a Melling transform like that, and then you get, let's say, analytic continuation, right? So if someone gives you, some infinite product and tells you, well, actually, you can write it as the Melling transform of something, then you know a lot about this function that you cannot see from the infinite product, right? So the question is, can we get such functions from the geometry? That's really, if we can, that would be wonderful.
But
So
I didn't understand what is the point of getting rid of the t if you still have the t to the s in the integral which will turn into log q to the s.
I want to write a measure over z. That's kind of what I'm trying to do. So I'm trying to write some measure, some element in this kind of z function analysis that will specialize to different measures. So will give me both kind of the p-adic zeta measure and the complex zeta measure. And then kind of I need, characters look different, but you can get functions in different way. But so it's more like kind of looking at some algebra, what this germ really is some algebra of measures. And again, you see that for people who work in the p-adic setting, usually you do radius 1, right? So you would not work with the germ, you would work with analytic functions of radius 1. Here I'm working radius 0. So again, so an easy calculation, I don't really have, well, you can just calculate that, well, you notice again, this is the standard, but if you write 1 plus t to the a minus 1 is kind of at times 1 plus t and some function of t, right? So here, I mean, everything, this is of course just a polynomial. Then you just calculate, and if I define something like h, a of q, to be exactly this 1 over q minus 1 minus a over q to the a minus 1. Remember that q was this 1 plus t, it's the local parameter at 1. Or maybe better if I write it in the t variable. This is 1 over t minus a over 1 plus t to the a minus 1. You just expand this and you see that this does belong to the germ. Except that you need to invert a.
Sorry, I'm not, is this definition of H? What does this have to do with?
Yeah, this is the definition of H.
Okay.
Yeah, I'm defining H, actually, it's just F with a different coordinate. And I'm just saying that if you just use this and expand this, you see that it belongs, well, you need to invert A, but it belongs to this germ. Right? So again, in this bornological category, I mean, this is some bornological ring, which then you can base change. So you can base change to C, or you can base change to kind of QP if A is co-prime to P. Or ZP, let's say, A is co-prime. So the point is that you get some expression over Z that kind of sees both, again, there's nothing strange going on here, it's just kind of the observation that when you expand this usual thing in p-adic kind of measures, this has coefficients which are, well, almost integers. I mean, you might have A similar denominators. So, but it also lives and kind of has the correct growth conditions over Z. So it kind of base changes correctly. If you have some the Richelet character, you can do the same thing if you add a few roots of unity. You can also, and something I didn't discuss is, of course, for any number field, if you look at its ring of integer, it's has a natural kind of canonical Banach ring structure. So we can tell the story also there. Do function analysis over, let's say, Z with some roots of unity or other kind of rings of integers. And then kind of another thing you can do, which you can also look at this function H. Well, you can play, I mean, when you start thinking about it, you can start playing a lot with this and write lots of expressions over Z or some versions of maybe localized away from some primes. converge. And another expression you can look at is this. You'll see soon why I'm interested in this. Another interesting thing that you can do, if Sam mentioned divided powers, is kind of course, if I look at this expression, I can write this as log q over q minus 1, right? And you can ask, well, how can you introduce log q to the business? Well, that's kind of easy. You can formally add a symbol called log q. In the following way, I can look at this divided power algebra, but take a completion of it, and that's kind of like the Borel transform algebra. So I'll look at some infinite sums, let's say ai x to the I over I factorial, again with some convergence conditions. Essentially, I would want that the sum of ai over I factorial. And you can put different, well, let's say you convert this for some radius. And then this ring contains kind of the formal exponential, which is just the sum of xi over I factorial. And then I can look at just, say the ring, the dagger ring over Z, or I join log Q. So this is just kind of, I take a germ, and I look at these divided powers, and I just mod out that the exponential equals Q. Right, so I just added log Q, of course, or Q is 1 plus T. So this adds log of 1 plus T. Now, if the point is that if I had, if my Banach ring contained rational numbers, I could just write log 1 plus T as it is, but it will have some convergence radius. But in this way, you can do it over Z, right? So actually, this expression lives, right? So just log Q over Q minus 1. Well, you need to localize this with Q. This is this robber ring type, but the final is there. So so again, you get this expression that I can now base change it to C, I can base change it to QP. Again, I think the reason why people p-adically often don't work with these things is because, again, the insistence of radius 1, right? If you use kind of different radius, in other words, you usually look at some algebras that have to do with like measures on the disk of radius 1, and that puts kind of growth conditions that the kind of things I'm looking at will not, you need a germ or kind of a smaller radius. But if you take a smaller radius, this means that it's still an algebra distribution on some bigger disk, or maybe, like you said, I mean, the germ is just on all analytic functions, rigid analytic functions. So these are the kind of games you can play with this. Start writing integer expressions of some measures. Okay, so what's global Hodge theory? It's something very simple. So it's just the following thing. I take this dagger disk. I told you that it has an action of this GM arithmetic analytic, right? And just to recall, this action is just the one coming from Q goes to Q to the X. It's a nice stack in this kind of analytic geometry over Z. And what I didn't tell you is you can, for any nice stack, there's a nice category quasi-coherent sheaves over it, which satisfy kind of descent and all the properties you would like are true. So let's say these are, I call these things kind of global Hodge modules, because if I base change this to, let's say, ZP, I get something like a WAH module. If it's a, let's say, vector bundle on this thing, if you just look, this disk will just become some formal power series over ZP, and this is the usual formula for how kind of the phi gamma acts. So kind of over P, you get like phi gamma modules, and over the complex, you get something like essentially a filtered vector space.
But do you really have V and gamma?
Yeah, because the formula always is just kind of 1 plus T goes to 1 plus T to the lambda. When lambda is P, that's Phi, and when lambda is kind of in ZP cross, that's gamma. So yeah, so if you get, again, it's not it's not the usual definitions. I'm using a germ. I mean, there's something interesting going on here, in terms of you thinking about the far-containing curve, right? If you start with let's say the rubber ring and you take some perfection of it, you essentially get the far-containing curve. But the thing is, because it's radius 1, whenever you take a piece root, you need to take a smaller radius. The piece roots are, but in the germ, this is already perfect. So it's an interesting question, kind of to also p-adically kind of replace the rubber ring by this kind of rubber ring of radius 0 and see what type of p-gamma theory we get. So, okay, so this is some kind of, let's call this the category of global Hodge structures. And the question is, how do we get objects in it? So one thing to notice is that, well, one easy thing you can do is you can write line bundles. Since kind of, let's say, a line bundle on this germ is trivial, then really line bundles are just given by some functions, let's say f, it's called x and q, in this int stable tensor kind of the dagger algebra, which satisfies some co-cycle condition, and write clear co-cycle condition. And then kind of, if you want, trivializations of a line bundle, they will be given by functions of the form kind of h into the x over hq, when hq is an invertible germ. So this is how, and that's the reason why before I also mentioned these kind of examples, right? So you see that if I have like these functions of q, they correspond to trivializations of a line bundle, which again, in this kind of philosophy of what L functions or L measures should be, there should be some trivialization. But my point is that you do see these kind of expressions that might be zeta or L measures as trivializations of the line bundle. So that's another thing you can see. And now the question is, how do we get such objects? Because actually, if you try to write down such global objects, it's not, using the standard theory, it's not clear because the formulas often depend on P in a way that it's not clear how to write these analytic formulas that somehow. So for a long time we were stuck kind of, this is a nice category, but how do you get objects in it? But then, this is why I introduced all of these objects, this GA. So here's a cohomology theory. Which is really easy to write down. So suppose I have this scheme of the set. Yep.
I think you're saying the global Hodge theory category. What are the categories it maps to, like for p-adic Hodge theory and usual Hodge theory?
So you can base change this to ZP or QP or to the complex numbers. So the way I think about this is kind of, I'll take a bit more time if that's okay. I mean, finish soon. But in the one kind of old way of thinking about motives was just as a family of realizations, right? Now the problem with that is that kind of in some sense there's too many options, right? Like the morphisms between two, it's huge. Now I'm saying, well, really it's a family of realizations, which is kind of an analytic family in some parameter. This is sort of what this is, right? So this is kind of it gives you an analytic family over Z. So when I can base change this. So, if you write down, like you see here, these formulas are defined with kind of integer coefficients, and then you can look at them as kind of giving you formulas, analytic formulas over ZP and also over the complex numbers. So in that sense, it's kind of an analytic family of Hodge structures, p-adic and complex.
So does it have like a literal functor to either like complex Hodge structures or?
So you definitely get a functor to filter vector spaces. You have a bit more here. So it's not, but in the p-adic setting, this is much more based on the p-adic thing, and there you clearly you do get the Wach module over ZP. Yeah. Or, yeah, you you can do other versions. I mean, I can also do the robot. I can localize the T and get some other, there's some interesting questions there, but yeah, you can at least you get wash modules for each P. So suppose I have this kind of scheme over Z, I can associate to this multiplication. Again, this is just a general nonsense kind of thing. So this now will be one of these objects in this analytic geometry over Z I told you about. And I'm defining kind of its essentially like invariant loop space. So this will be just maps from this GA all the arithmetic, analytic filter to X analytic, right? And this, because this, this lives over the disk. Well, sorry, now mod out by this action. Okay. And this thing also, it also maps kind of to the dagger disk, right? So essentially, this thing is just kind of, it's a family of groups really over the dagger disk yeah, that's what it is. And let's call this map P. So this is kind of this arithmetic loop space of X, or analytic arithmetic loop space. And from what we said before, kind of GM, arithmetic, analytic, acts on both these things in a compatible way. So, well, here's the definition. I define kind of my cohomology theory, make effects, just the derived push forward, and we can go into discussions, there's kind of different versions of quasi-coherent sheaves. You can.
What's the map P?
Oh, just because this thing lives over the disk. So kind of for each fiber, I mean, you have the mapping space, right? So just this collection of mapping spaces put together. So I just kind of push down the structure sheaf of this space, the derived push forward. And again, by definition, this gives you such an object, right? Well, I can mod out by, well, you get the GM equivariant sheaf on this dagger disk, or if you want, it's a sheaf from this quotient. So that's your cohomology theory. Now, the point is, if I look at this thing locally, let's say over ZP, then, over ZP, this type of object, well, without taking the equivariant, there's this work of Toel and collaborators. So this gives you, so the point is that this is kind of, actually goes back, I guess, to Grothendieck. The integer valued polynomials, that's the schematization of the circle. So in this way, you get a filtered circle from this. So this GA is essentially a filtered circle. And we know that over ZP, and this is where kind of, it's a nice thing that ZP is finite type over Z, because the base change of this then will be just the base change of the two objects, the mapping space. So you get the form, so this is some kind of a filtered cyclic cohomology construction. This is what it gives you. So kind of I'm saying that in this way you're seeing kind of, well, I'll maybe tell you very soon, from this you can get some kind of symptomic cohomology, and it kind of sees, you're seeing the phi gamma structure on these derived deRham type things.
So when you say that it's
Yeah, I know.
when you say it's schematization of the circle, you mean that it's a distribution algebra of formal of the GM group. Yeah.
You can say, yeah, you can say that. So I'll just finish, just another, sorry for taking too long, but just have some questions. So I told you this is work in progress. So, we can define all of these things. It's all nice. There's nice formulas, but so here's some kind of questions. If I'm on the optimistic day, I think they're true. If I'm sometimes less. So first thing, kind of, I can define, like I can look at some, those kind of Tate twists. I can look at xi of, Oj to this cohomology theory. I can look at, so kind of define the absolute global Hodge cohomology in this way. So, and then my question is this motivic character of homology? There's kind of good reasons to think it is, because it does, again, you can write this Z as a union of Z triv with the Archimedean part. And you see that sort of you get, on the Archimedean part, you get something that resembles the lean homology, and then on the Z triv part, you get, so in this thing, you can write it as sort of cone of things that look, so it's a reasonable guess. I don't know if it's true. By the way, I mean, if this is true, so kind of, I can just look over Z triv, just the non-Archimedean part of this. So I'll get just a motivic homology. And then another question is, well, if I look at this homology theory over this stack, is this thing a cyclic after some base change? So by this I mean, you know, you can maybe add some roots of unity, or more generally pass to some kind of ring of integers of some number field. I can add some logs. I can, you know, the sort of things I did. Why would, well, because if it does kind of become a cyclic, then what we know, we can take its determinant over this base chain. This kind of canonically trivializes. Says giving us this age of Q from before. So if this, I won't call it a conjecture because I don't really have evidence, but if this question turns out to be true, you have a machine that takes a scheme and gives you an analytic function, right? Which really knows about all these p-adic Hodge structures as well. It's not, of course, not just arbitrary. So, and then, you know, if this is true, so you can ask, is this the measure giving a survey L function? Right? Yeah. If I'm very optimistic, I would say yes, and that would be amazing, because then we get analytic continuation. And also, actually, I think you can get by using on this space, right? I can use kind of SARE, or what you might call Poincare duality, maybe a functional equation. So these are the two main. So yeah, you see, kind of, if 2 is correct, then we get lots of interesting applications to number theory. And of course, this function also knows about all the values of negative integers by taking its derivatives. So it's more, and these derivatives would be related to the p-adic Hodge structures. And if the first question is true, again, being very optimistic, then this would tell you that this category, well, I think you can probably deduce from this that this category is equivalent, or at least over Z triv, to mixed motives in the derived category of this thing. And then you get the natural T structure on this category. And as we know from Benningson, this kind of gives you all the standard conjectures. So that's why I'm saying, if I'm very optimistic, and the questions, the answers to this is yes, and then we get some nice stuff. But I don't know, so it's in progress. Thank you.